Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Dimitris Christodoulou with us today. Hello, Dimitris.
Oh, hi, Professor. Thank you very much for the invitation. I'm very happy to be here.
Well, thank you so much for being to talk about your lovely research note. And Dimitris, where are you located right now?
Right now, we're in the middle of the summer, so I'm back home in Greece.
Greece.
Visiting with friends and family.
Very nice.
I will stay on for a couple of more weeks before I come back to the US.
Very nice.
The research continues uninterrupted.
Whereabouts in Greece are you?
I come from central Greece, town very close to Mount Olympus.
Okay, very nice.
We have first rights to Mount Olympus.
Very cool.
In my hometown.
Very cool. Very nice. And it is June 29th, 2023, as we record this one. So greetings from Greece. And I'm in Phoenix, and it is definitely hot in Phoenix. we have hit the power switch, so we're good and warm. Indeed. And Dimitris, what do you like to do for research?
We have a pretty decent group at UMass Lowell.
Okay.
And in collaboration with Silas Leko, a collaboration that has been going on for many, many years, and other outside collaborators, we have quite spread out our research interests. We have students also working in high mass X-ray binaries. This is one of our major projects.
Okay. And
it's been going on for 10 years. We're trying to create a humongous library of X-ray binaries, covering all of the Magellan clouds. And then, of course, some of the famous sources in the galaxy, and from all the different telescopes, the X-ray telescopes. Right. And we're trying to process the data in a way that we can give it to everyone else in the community in a ready-to-use format. That's one of our major projects. We have one student working on gravitational lensing, which will be today's topic. And we also have people working on modified gravity and alternative theories and all that.
Yes, very cool. Very nice.
Oh, yeah. Our tentacles are reaching many different topics of contemporary astrophysics.
That's good. Good. High energy. And that is going to bring us to this very awesome research note. It is open access, people. It's the open access era in 2023, and you can go grab a copy, go get one. Clarifying the optical thin lens equations of gravitational self-lensing. And Dimitris, take us away.
Okay, yeah, this is a brief note that we wrote recently on something that we didn't actually plan to investigate. It just came in front of us. As I said, one of our projects is gravitational lensing. It's been going on for 3 years now at UMass Lowell. And we do have a result, not in this paper, that is extremely important to the community in trying to find compact objects that are doing self-lensing, going in front of stars in the galaxy. Okay. We found, we looked at the Kepler data, the Kepler Space Telescope, and we found, to our surprise, quite a few of them, one at a time, and all those lensing signals were fake. And well, something didn't sit well in the beginning. We eventually figured out that there were asteroids that were crossing in front of the stars, creating a fake signal. And in the process of writing this up, we had to create a complete paper along with the theory of self-lensing. And then this other issue came up about the lensing equation and what does it really tell us and what does it mean? And how is it related to real lenses right here? How is it related to geometric optics right here on Earth? And because of the confusion in the field, we had to sort of investigate, go back. The first main point that occurred to us is that the term lens equation that people use in astrophysics is not quite precise. To tell you the truth, after a lot of deliberations, we decided that probably the right thing would have been angular lens equation, because what people call lens equation in gravitational lensing is an equation that involves angles or angular distances as these are projected in the sky. And it turns out that this is the major difference between earthly regular optical lenses and gravitational lenses. In gravitational lensing, as we all know, everything is projected up in the sky. So the astronomer has to deal with those projections up in the sky. And of course, it's a very natural thing to measure angular distances. It's pretty much the same thing as we do on daily astronomy, where we look at the angular diameter of the moon or the sun. So they're playing the same game. So the equation that they come up with, the main equation, should probably have been called the angular lens equation.
Okay.
So then we had to trace back to see when this term appeared.
Okay.
We put it somewhere like in the late 70s. All the people before late 70s did not use the term lens equation, although they were using the equation. And going all the way back to Einstein in the 1930s, Einstein didn't want to get involved with technicalities and names. So in his famous paper that started gravitational lensing, basically, he talked about a lens-like equation.
Right.
This is not happening anymore. There is nothing lens-like. There is a lens equation. It involves angles.
Right.
And one of the questions that I said to my students at the time was, well, okay, I understand that. I understand I have to work with projections in the sky. But since we think that there are properties of lenses associated with gravitational lensing, I would like to know what the geometric optical equation, lens equation, looks like in this case.
Okay.
This is a point that astronomers may not be interested at all, because as I said, they have no way out of projections in the sky. And what I'm asking now is I'm asking about the depth dimension on those gravitational lenses, where the images form and all that. But as we all know, no matter where they form, eventually those images will be projected up in the sky. But anyway, I thought it was interesting. And it also helped really relate the regular lenses and the gravitational lenses.
Okay.
And of course, there were other issues that you see here in this historical account that Lodge argued that this is not a lens. The gravitational lens is not a lens because the rays, the light rays, do not focus the same way. But of course, this is true, but it doesn't mean that the gravitational lens is not a lens, because it is like suffering aberrations in real lenses.
There you go.
Real lenses also don't focus all the rays in one location at the focus, but that's because they're aberrating. They have all kinds of problems associated with them, like astigmatism. People know about astigmatism and all that. So we didn't mind this very much. Okay. And we proceeded to write down the equation of geometrical optics, lens equation. And you can see the characteristic pattern in this equation is that it involves three reciprocal distances, not angles. You have the distance to the source, the distance to the image, and the focal length, F. And this is straight out of geometric optics. And then my question to my students was try to write this, to customize this equation, to apply it to the case of gravitational lenses, and let's see what it gives us. In other words, I was saying that let's ignore all those projections and angles in the sky. Let's see where this equation is going to take us. And of course, it takes us into 3D space, and it gives depth to those lenses that we cannot otherwise observe. So eventually I took this equation down for a binary, for a closed binary that you see in figure 1. This is the main figure, really, that explains the geometry of what we were dealing with. You have a binary star, you have a luminous star, and then you have maybe a compact star, the little one over there, L. The compact star is the lens. And they're orbiting around each other. You have separation A. They're orbiting around the center of mass, as you can see. And the observer is very far out on the left. And the important thing to realize is, of course, this is not in scale. The diagram is not in scale. That the separation A is much, much smaller than the distance to the observer, which I call DOL,
Okay.
observer to lens.
Okay. Yes.
And
Okay.
and the angle psi that I have here in this diagram is also supposed to be a very, very small angle
Should be,
up in
yes.
the sky as the orbit. So yes, and then of course I also projected the star down. And, you know, I also put down the image plane, and you can see the 3D depth now,
Yes.
because you have this plane of the source onto which I projected it down to the horizontal line, but you also have another plane a little bit behind the source, which is the image plane.
Yes.
So in this type of setup, the main lens equation from geometric optics is written as you can see, and the new variable that enters this equation that you don't see in standard lensing is DLI. It is the distance between the lens compact star, the lensing compact star, and the image plane.
This distance right here. Yep.
Yes, DLI is the new thing. This, of course, is not measurable because we cannot perceive depth behind the sky, so to speak.
Yeah.
But again, we have theory on our side.
Right. I'm with you.
Yeah, we can proceed. Yeah. In the next step, I solved this equation for DLI. It is the important parameter. I solved it. I made an approximation as to the fact that the observer is just very, very far away from the binary.
Right.
And I got a negative value for DLI, which tells us immediately that the image is virtual. Of course, we know that. We've always known that the images that we see with telescopes are all virtual. Yes. So this is just a quantification of the phenomenon. And it tells you that more or less DLI is pretty much equal in magnitude, in absolute value, to DLS. So the image will form slightly behind the source plane. The image plane will be very close.
Yes.
And they both will be, of course, very far away from us, the observer. So that was like the first part, and I was happy with it. And then I came up with this idea: maybe we should call this the lens equation and call the other one the angular lens equation.
Okay.
But we looked in the literature now. We didn't look for this DLI thing because it's not there. But we looked for other equations that people might be using that involve reciprocal lengths that might look like a lens equation. I was looking for the geometric optical lens equation.
Okay.
Even before I did this calculation. And I found one that looked like it. And then I realized after a while that this is not like totally fake. I mean, people are using it for convenience. They never called it lens equation or anything like that. But the way that it looks with the reciprocal lengths, it is very, very challenging. I mean, it looks like a lens equation, no matter what people call it. And then I realized that that was a disaster. Not only was this equation not a lens equation, but it came out of a renaming of complicated variables, but it was also a disaster. So technically, it is a mistake. It's an error that was committed for the sake of convenience.
Okay.
I wouldn't have discovered it if it didn't look like a lens equation. So here's the story. I'm taking these reciprocal lengths, 1 over DOL minus 1 over DOS. And I work out the fractions. Okay. I do the approximation of the small separation compared to that. Yes. And I find this thing that this is a rate. It has a distance at the top, and it has a distance squared at the bottom, which is like an area. If it's a distance squared, it's like an area.
Yeah.
But because of the units, length over length squared, people realized immediately they can call it 1 over D relative. Some people call it effective. Some people call it relative. Okay. This simplification should have been forbidden from the outset. It should never have been done. We should have stayed with the original difference of reciprocal lengths. Okay. We should have written down our equations bigger, and some people did. don't get me wrong. I mean, some people did stay with that. They didn't use D relative or anything like that.
Okay.
Makes the main equations awkward, to say the least, but at least they're technically correct. Now, what is wrong with calling this D relative? In the paper, I tried to talk about math and rates and all that. I didn't take the easy way out. I wanted people to understand what is wrong here based on like fundamental algebra. But before I go into the fundamental algebra, let me just tell you right away that I personally know of 2 examples in which people did the right thing and they did not do analogous simplifications. One of them is, of course, the famous Hubble constant, where the kilometer in the numerator and the megaparsec at the bottom do not get canceled, do not get converted to the same length and then canceled. But we never do that. We never express the Hubble constant as 1/2. And the other case comes from high X-ray binaries that I told you, where on many occasions, after a lot of hard work and many difficulties, we managed to calculate the famous P dot, which is the time derivative of the change of the spin period.
Yes.
When you see people writing down the results on P dot, they always quote a unit, second times second to the -1.
Yes.
They never cancel the seconds to tell you that this is a pure number.
Yes.
Why do they do that? Well,
Because
it's an algebraic thing.
Yes.
When we create those fractions, we create the rates because the units do not cancel identically at the top and the bottom like in a ratio. In a ratio, the units cancel, they go away, and then we have to use language to tell people how we got our ratio. I divided, I don't know, 2 meters by 3 meters, and I got the ratio first. But here, we're dealing with the rates, with quantities that have different units. If you cancel and you simplify the units, you're hiding effectively from the reader the origin of those quantities that you divided. That's why we never do that. We want, when somebody sees, for example, the Hubble constant, we want them to see kilometers per second in the numerator, which is a unit of speed, of course, divided by megaparsec, which is a unit of length.
Right.
No simplifications. So the same thing should have happened here, but people took the easy way out. As I said, they brought in this DRL. Equation 4 shows you now 3 reciprocal lengths. DRL was created by renaming. It simplifies the equations, but it gives the wrong impression.
Yes. Right.
And also hides the rate that you see, the DLS over DOL square that you see. It's hidden now. Everybody thinks that
it's
they're
not a
dealing with
distance per unit area.
Relative or effective or something, when no such thing exists. Some people called it, by the way, effective D in passing. They just wanted to do away with it and just use it. And I tried to put it in the diagram of figure 1, this derivative, and it leads to nowhere. So there is no such thing as an effective distance in figure 1. I could not, I mean, if I plotted the relative starting from the observer, it would be another mysterious arbitrary point somewhere along the horizontal line that means nothing. It misses the binary completely and doesn't mean much.
Okay.
So I thought that was interesting too, that the simplification should have been pointed out that people shouldn't do that. I mean, sometimes the equations are big and we have to accept that.
Big equations are big equations.
Exactly. So then I proceeded in some very small subsections to tell you that if somebody adopts DRL, like Gould, for example, had a system of certain units and stuff, then DRL would take over all the main equations, like the Einstein angle, the Einstein radius. It would be indispensable. That thing that was artificially created could have become indispensable in Gould's notation. For one reason or another, Gould's notation never caught any steam, so people don't use it today. So this never happened. We're well off and protected, and our equations are good in gravitational lensing. And that's what this shows about Einstein radius and all that. And of course, also the approximations that you see here are used by people. They all rely on the fact that the separation rate is much smaller than the DOL, distance
Right.
between the lens.
Yes.
So everything is normal.
Yay.
And I closed this very brief note, really, with saying that all this was a geometric. Well, first of all, I paid homage to Witten Mao, who didn't have to deal with any of the stuff that I mentioned above, because they had a very smart way of dealing with gravitational lenses. They created two Einstein radii, and of course, the definitions are crystal clear. And I think it was a very smart thing to do. And they didn't have to deal with all this stuff that I mentioned above. Then, of course, I said that I never actually used the main coefficient, the famous 4gm over c squared square root. This is Einstein's quantification of the deflection of rays. I did a geometric calculation. So my calculation doesn't depend on using general relativity or using Newtonian dynamics. As we all know, Newtonian dynamics gives a slightly different coefficient, so it's off by a little bit. But the above geometric investigation doesn't rely on that. So it's good, no matter if you want to do Newtonian approach or Einsteinian approach. And at the end, I threw in something else. I thought I had to make a statement. I don't know. The lenses that I talked about are stars in our galaxy and in binaries. And one of the components of the binary is a compact star, hopefully, and goes in front of the star. And we get what we now call self-lensing. But the lensing did not start with systems like that. It started with quasar lensing, which is a completely different setup. What's the problem in the quasar? What's different? I mean, there is no problem. It's just different. In a binary, the two components, the lens and the source, are very close to one another, and we're somewhere far away observing from far away. But in quasar lensing, the actual quasar, the source, is very, very far away out in the universe, and and very far away from the lens too, that we see.
Yes.
So I cannot longer assume that the separation is much, much smaller than the distance to the observer. Those distances have grown to be very big. So I looked at the geometric optics again to give me an idea how I could write down DLI, the famous DLI, which cannot be observed. Again, out of theory, how could I possibly get it for a very, very distant quasar? And the answer is that the only way I can do it, by the way, I'm not the first one who did that. Professor Nolte did that in 2018. He thought it was a very cute result and put it in a book, in a fantastic book that he wrote, not only about lensing, but about many other different things. Galileo Unbound. I strongly recommend this book.
Okay. There's a thumbs up.
He did mention about the image of quasars that are forming in front of the lens, meaning, behind as far as we're concerned. We are behind the lens, so the images go behind the lens. Anyway, so in order, but the interesting thing is that in order to derive this same equation that Professor Nolte gave us, I had to use a divergent lens. So F now, the focal distance is negative, as you can see here. And it shows, so the lens is not a magnifying lens. The quasar gravitational lens is not like a magnifying lens, which is the previous case of stars. It is a different, it's a divergent lens that, linearly speaking, optically speaking, does not amplify the image. It even makes it smaller, but it brings it so much closer to the lens. So the quasar is like way out there. On many occasions, we can't even see it. But the image is very close to the intervening cluster that is doing all the lenses. Well, not exactly the same distance. As I say, it's twice as far behind the intervening cluster, but this is still close. It's closer, it's much closer to us than the original quasar. So that's what we learned from this equation.
Very cool. Very cool. Very cool. Let me check out that Nolte reference. It's okay. Very good.
Yes, that book is highly recommended. It touches on many different aspects of physics and astrophysics.
Cool.
And anyone can read it. You don't have to be a specialist on something to read it.
Okay.
I think it's really good work.
Very nice. Very nice. Dimitris, thank you so much for sharing your research note with us.
You're very welcome. You're very welcome. It's my pleasure.
Sure. And so do you think there's anything to do with this? Is this a matter of
it's not going
educating the community
yes.
or things along those
You're
lines?
right. I should have said that. It all ends up being a peripheral issue or a tangential issue to gravitational lensing. It's not going to change observations. It's not going to change the way that they process it. The reason is that we're bound by the sky and the projections up in the sky. This will never go away. It's the nature of our observations. Everything gets projected up in the sky. So this ends up being like a little side note that is trying to draw a connection between gravitational lenses and optical lenses. And if nothing else, at least it says that the name lens in gravitational lensing is not a failure. It's not bad, because there are certain similarities that can be found between the lenses, despite the fact that the approaches are different. You approach optical lenses in the lab one way, and you approach gravitational lenses the way that we all know. So it makes a connection. It justifies the name of gravitational lenses.
Cool.
But nothing is going to change in the way that things are done in our investigations.
Love it. Very cool. Dimitris, thank you so much for sharing your research note with us today. That was awesome. Very good.
You are very welcome. Anytime.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.